Hey, welcome back to Introduction to Computer Networks at NTU. I'm Polly, your instructor. All right, so beautiful weather again today. And you know what? Normally we have nothing more to say on Thursday, but today I would like to remind you guys of a little bit more things. Hi, Sophia. Hi, good morning. I know it's a little bit hard to gather all of you in the morning, but it's okay. Hey, we can all watch the playback. Hi. Yeah, so I do have two more things I want to announce or remind you guys. First is PA7. We know PA6 is straightforward, right? But PA7, it's due really fast, next Saturday, in fact. And the reason that I want to remind you about PA7 is that starting from PA7, in fact, 7, 8, 9, they are in series. And in the end, you'll be creating a secure web server using the building function in Golang. All right. It's surprisingly easy, but the set of function calls you'll be using are completely different from what you've learned in PAs 3 to 6. So when you're learning something new, it's by default time consuming. So guys, you want to start early working on PA7 and particularly PA8 because PA8 is the third hardest PA in the whole semester. All right. Hi Justin. And Maria. Another thing, exam 2. It's coming up on week 12. Okay, so hey, where are we now in terms of time? Okay, let me take you to the course page. So this is where the golfer is. And if you scroll down, you should see a link schedule. Yeah, now let's review the schedule. All right, we are currently at week 9. Hi, Josh. Hi, Nicholas. And I think Zhexuan is Emily as well. We're currently week 9. This is the beginning of the second half. Hey, you've completed one half of the semester. Good news. Good morning, Miguel. And you see, today, indeed, we'll be talking about reliable data transfer of TCP. And we'll also talk about flow control and connection management that we mentioned yesterday in the overview. Today, we'll possibly start talking about what congestion is and how we potentially address congestion. So congestion, bad thing. So this Saturday, you know already, PA6 will be due, and next week, PA7 will be due. Okay. The next week, Holly will be on conference travel, and there'll be no live sessions, but you do have some assignments you need to watch. 3 hours of video, and during these videos you will see quizzes popping up. You will also need to complete those quizzes as well. Okay. And good thing is that during that week there are no PA assignments due. Okay. But you do want to use the time to start working on PAA because right after Polly comes back, we'll have the second exam. That's on November 23rd to be exact. And the week after that, PAA doing. And back to back, PA9 will also be due. And just 2 more weeks, the final exam. I know. You were going like, wow, I didn't know these are coming. Well, they are coming. And the reason that I'm spending time today is so that, hey, you get alerted. Okay? Is exam 2 cumulative? Or, very good question, Sophia. Exam 2. I did plan to talk about this. Even though exam 2 is going to be on November 23rd, you see also that in the 11th week, we'll start talking about chapter 4, the network layer. But in exam 2, you'll be tested only to the transport layer. Okay, which means it will contain the content from after exam 1 to exam 10, the end of chapter 3. Okay, so after exam 1 scope until the end of chapter 3. Similarly for exam 3, The scope will be starting from chapter 4 to the whatever we end up with at the end of the semester. Okay, good. All right, with that said, hey guys, careful. Especially towards the end of the semester, you will see lots of deadlines and you will feel like you did not expect them, but you are actually informed at the beginning. Okay, and people can be forgetful as we get busy. So, yeah, so now you are aware of all these deadlines coming. Good, so finally we'll talk about the reliable data transfer of TCP. You will see in the video that, hey, it looked familiar because if you pay attention yesterday, TCP's reliable data transfer is just like go back in, but with better bandwidth efficiency, recall? We don't drop the packets that arrive out of order, we buffer them. So we don't have to retransmit those packets. And towards the second half of the video, you will see that poly represent the finite state machines, right? Circles and arcs in a different way. It's a little bit more descriptive. And then there's a version coming out of that description that looks just like a pseudocode. With that pseudocode, any programmer will be able to follow and implement TCP. So, first video, about 7 minutes. And here, RDT of TCP. These are the characteristics. First of all, it's pipelined. So we send packets back to back in TCP as well. We could have multiple packets in one flight. And the acknowledgement is cumulative, meaning the sequence number in the ACK indicates all the packets below that up to that number are received correctly. And there's only one retransmission timer for the entire flight of packet. And so when that timer times out, then we retransmit the flight of packets. So up to this point, you will probably guess TCP's RDT looks very much like, yep, GBN, the go back in. Now the slight difference is this. In TCP, the RDT adds a little bit something so to speed up the retransmission. And that is a special condition when the sender sees a certain number of duplicate ACKs arriving quickly. Yeah, retransmission timeout, let's not wait for that. That's quickly retransmit. Okay, so this is also called the fast retransmission mechanism. So this is something that's a little bit unlike the standard go back in, but implemented in TCP. Right. Next are the finite state machines of the TCPs. To make it simple, let's ignore the dupe ACK part, okay, the fast transmission part, and let's not talk about the other mechanisms we have not yet discussed that's implemented in TCP. If you're expecting TCP sender looks very much like go back in sender, you're correct. First transition is what? The get call from above transition. Okay, receive data from application. Okay. So in TCP sender, we generate the packet, assign the sequence number to the packet, of course also calculate the checksum, and pass that to the lower layer. So it's essentially the UDT send call. And we check whether the timer has already been started for the flight. If it does, don't do anything. Otherwise, if there's no timer currently running, we're sending a packet, then this must be the send base. Start the timer. And then we increment the next seek num. But in TCP, we are not counting packets, right? If we are counting packets, we add the sequence number by one packet. But here, we are counting the bytes. So we are adding the number of bytes in the data in the packet we're sending out. Now, you see here, I'm trying to be a bit lazy. I did not do the window size check, okay? But in TCP sender, there's also a window size. So there should be an if condition here before creating packet to check whether the next seek num, okay, is still within the window limit, of course. And next, this is also a familiar transition. This is the transition when the sender receives an ACK. Well, similar to go back ends, transition receiving an ACK, that's extract the sequence number from the ACK packet. Now, the action of TCP sender here is different. Only when the sequence number is larger than the send base, meaning this is a new ACK packet. So the sequence number here is something that has not yet been acknowledged. Then we send the send base to the new sequence number because now acknowledgement is received. Sender should say that, that's slide the send base over. All right. Now, if there are currently not yet ACK packets around, then that's restart timer. So we'll be starting the timer for the new send base. If there are no outstanding packets, so if there are no not yet acknowledged packets around, then let's simply stop the timer. Because this act here, acknowledges all the packets that are waiting to be acknowledged. All right? So, hey, looking very simple. That is also saying when y here equals the send base, we do what? Nothing. So if a duplicate act is received at the TCP sender, hey, timer does not get restarted, unlike in go backend. Yeah, even though the sequence number is the same, timer gets restarted, refreshed. Okay. And the third transition, again, very typical, this is the timeout transition. So when timer times out, retransmit the entire flight of packet from the send base, and then start timer. This is actually identical to go backend. Yeah, in go backend sender, there's actually one more transition, which is doing what? Checking whether the ACK is corrupted or whether the ACK is a NAC. Okay. In those cases, we do nothing. But you see, when ACK is received, do these. And when the ACK is new, is doing this. So all these other things do nothing. Is just, saying default actions all ignored. Okay, so from now on, if you don't see any other conditions being listed as a transition here, that means they will be just ignored. Now, this is just another way of writing the finite state machine, but in a pseudocode form. So we switch, different events. There's the data received from above case. There's the timeout case. There's also the receiving of an app packet case. So receiving data from app, generate packet, set the sequence number in byte count, and start timer if there's not one yet running. Just to make sure that you set the timeout interval to what? The estimated RTT plus 4 times the deviation of RTT. In timeout here, if it is triggered, then retransmit the whole flight of segments and restart timer. Receiving an ACK, extract ACK number. If the ACK number is new, meaning it's acknowledging something that has not yet been acknowledged previously, then update the send base. So we slide the window over. We restart the timer if there are still unacked packets waiting. Otherwise, stop timer. Right? These are the only 3 events. If there are other events occurring not fitting any of these events, ignore. If you're not quite convinced the previous slide is the pseudocode, this one should convince you. Okay, so what I'm listing here, typing up here, is essentially what the finite state machine is telling. Initialization, and this, it's gonna go forever. It's looping forever, just like every server here, right? Waiting for an event to occur and take the actions correspondingly. It's a switch essentially on the events, and there are 3 different events: getting data from above, timeout, and receiving an ACK. So, from a finite state machine, you can actually convert it to a pseudocode, give this to your programmers, then you get yourself a TCP sender implementation. Right? So, being able to write out from the thinking, from the designing of TCP sender to the finite state machine is essential because, that drawing the finite state machine out of your thinking process is simpler. Okay? Trying to write the pseudocode out of the thinking process, just too challenging. Okay? Once you get the finite state machine, then you can gradually transition that to pseudocode. And there, you are one step closer to getting an implementation of what you were thinking about, what you were designing about.
All right. With the PA5 you guys have worked on, you see that Polly said it at the very beginning of the semester that the kind of programming we do here in this course for computer systems in general are not like the kind of programming you do for the data structure course or the regular programming language courses that they've taken before. The goal here is to make sure that it will run as long as possible, especially a server program. Okay, so quite different. Okay, the idea, and therefore the pseudocode always have an infinite loop. Well, actually, not always. For servers, the pseudocode always have an infinite loop. Okay, now next, let's exercise TCP's RDT with a few examples.
As usual, let's walk through a number of examples and exercise our understanding of the TCP's sender-receiver mechanism. So first scenario, very straightforward. We do have a data center here. Host B is just receiving, sending acknowledgements. Host A here sends one packet starting from sequence number 92. It's carrying 8 bytes of data. Therefore, the ACK should be carrying the sequence number 100. Now, this ACK packet is lost. Okay, so host A here waits until timer fires. And so the same packet is retransmitted. Finally, ACK comes back, and the next packet will go out carrying sequence number what? 100. Because the ACK number here is counting to the last byte plus 1. So 92 is the first byte. The last byte will be plus A subtracting 1. But ACK is adding 1 back here. All right, so it's 100, and adding 1 back is also a way for the receiver telling the sender what is the next byte expected, what is the next data byte expected. So the packet coming out from the sender next is definitely going to be the same sequence number in the ACK received previously, right? 100. And the second example, again, host being the data sender, host B being the receiver. This time host A sends 2 packets back to back. First, starting from 92 and then carrying 8 bytes of data. So we know that the last byte is 99, therefore, the second packet starts from 100. And 20 bytes of data to be carried, so the last one is what? 119. And therefore, the ACK packet for the first one is last byte plus 1, 100. The ACK packet sequence number for the second packet is last byte plus 1, 120. Now, in this scenario, we are trying to demonstrate the strengths of using cumulative ACK. That is here. If one of the back-to-back packets that came in earlier, ACK is lost. But as long as one of the later one arrived, because 120 here is saying, server, you know what? All the packets before the sequence numbers are acknowledged, whether you receive an ACK packet for an earlier sequence or not. So to this point here, sender host A here seeing, ACK 120, and therefore this packet and this packet both acknowledged. Okay. Therefore, there's no timeout is going to occur, and it's going to trigger sending of the next packet starting from 120. The third example scenario looks very much like example 2's, where we have a sender sending 2 packets back to back. Sequence numbers identical. Therefore, receiver here will be sending back ACKs, 100 and 120. The difference is this. Example 3 is to demonstrate a case where we have premature timeout. So that is saying the timer here, the interval is set very short, so timeout occurs before ACKs can come back. So first, timer occurred here. Therefore, timeout event in TCP senders trigger. Therefore, we retransmit all the packets in the flight. So sequence number 92 will be retransmitted. Sequence number 100 will also be retransmitted. Okay. Now, ACK 100, ACK 120 will arrive later. Okay. So when ACK 100 arrives at the sender here, Y equal 100, that is the sequence number in the ACK. The send base at this point is still 92. So Y is greater than send base. Therefore, we change the send base to the new ACK number. And do we restart timer or stop timer here? Well, there is still outstanding packet, right? Which is this one. So we cannot yet stop the timer. So timer is refreshed here. So timer for 92 is restarted here because, hey, timeout occur, retransmit everything, start timer. So there's already a timer ticking starting from here that is associated with sequence number 92. But here, we restart the timer, and this timer is associated with send base 100. When ACK 120 arrive here, we need to change the send base because it was previously 100, and the Y is 120, bigger than 100, so change the send base, slide the window over. Do we stop timer or restart timer? Well, there's no more outstanding packet because there are no more getting called from above. Okay, so, stop timer right here. The last point to make is this. When this data packet, sequence number 92, arrives at the receiver, receiver is going to see, data byte up to 99 received. But the thing is, the receiver has already received up to 119. So those bytes are extracted and passed up above. So that's not extract 92 to 99 and pass it above again. So this packet will be discarded. and an ACK will be sent back. But what is the ACK sequence number? Well, receiver has already seen up to 119. So what is the next byte expected? 120. Good thing is this, when ACK 120 arrives at the sender, well, y equal 120, which equals send base. Therefore, this packet is going to be what? Out of any of the 3 transitions, we ignore it. Okay, sender does nothing. The second packet here with sequence number 100 will also arrive at the receiver, and it's saying that it's receiving from 100 to 119. This is going to be ignored as well because, 100 to 119 bytes have already been passed up to the application layer. So another ACK, 120 is going to be sent back to the sender, and sender is just going to ignore it again.
All right, so those are to exercise TCP's RDT FSM. There's one more video regarding TCP's RDT. Even though that we say it's essentially go back end with the better bandwidth efficiency, but there are still some differences in TCP's RDT from go back end, and these are the differences.
And that was example 3. Up until now, the TCP mechanism we were talking about is very, very simplified. Okay, the examples we went through is very much based on the simplified TCP sender. The actual TCP sender is way more complicated. We have not yet talked about possible retransmissions when the TCP sender receives duplicate acknowledgements. We have not yet talked about extra mechanism in TCP's RDT that supports also flow control and condition control. So these will be coming ahead. But these also explains in example 3. You'll see in the textbook, the authors will describe it this way. When send base 92 expires, the timer, we only retransmit sequence number 92. But if you recall back, in go back end, we will be what? Retransmitting from the smallest sequence number all the way to all packets that have been sent before but not yet acknowledged. So that should include sequence number 100. And that is what I was describing, explaining example 3. The fact in TCP is this. There's something a little bit extra here. When timer for send base 92 expires, the sending window size at the sender there is also reduced to 1. That is saying, when the timer expires, the sender is going to retransmit, but the window size is actually limiting it such that we can only send 1 segment. And 92 is the smallest sequence number, and this is the only packet can be transmitted. And that's why, if you look a little bit careful about the sender's finite state machine we were talking about, and here it is, let's ignore all these other transitions that are not relevant. So we're experiencing a timeout event here. Okay? The description in the finite state machine says this. Retransmit not yet ACK segment with smaller sequence number. Now we read on the actions being taken carefully. You see, this is not in the pro form. So we retransmit just 1 segment and then start the timer for that segment. But this is really odd, right? So this is not really like go back end. This is not really like selective repeat either. This is in fact TCP's reliable data transfer mechanism trying to do a little bit of condition control. Let's define more precisely what TCP sender does when there is a timeout event. Note that this is no longer the simplified TCP. This one is actually quite realistic considering condition control. So in that, step number 1, the window size is dropped all the way to 1. As a result, we are only allowed transmitting 1 segment, a smaller sequence number segment. And then we're supposed to start the timer, but the timeout interval is set this way, 2 times the current timeout interval value. Then you go, hey, then what was the current timeout interval? Yeah, the current timeout interval is set here and here. In the transition where we get a call from above, at the transition where we receive an ACK packet from below. So you see the timeout interval are calculated this way. Yeah, this is what all those slides were saying, right? This is the equation we came up with. The average round trip time plus 4 times the deviation of the round trip time. Okay. Now, back to the timeout event. Setting the timeout interval to twice the current value. Oh wow, we were actually quite conservative here already, isn't it? That is what? Covering 99.99 something percent of all these RTT samples. And we are setting the timeout interval to twice that amount. That's way more enough. Why? The fact is this. Window size dropping all the way to 1 and timeout interval being twice super conservative are both to address the congestion that's occurring inside the network now. Because when there's a timeout, that is also saying there's no more X coming back. That is probably because data cannot go out. But TCP being a pipelined reliable data transfer protocol, oftentimes we're sending multiple of them out, right? If it's just, a sporadic drop, not due to congestion having consistent drops, then we should still be seeing, maybe a lower number of X, or maybe seeing some duplicate X, OX coming back. Not that we get no X at all and then eventually run into timeout. Okay, so timeout is TCP's way of saying that, let's assume now the network is congested. Therefore, let's be very, very friendly to the network. Okay, let's try to slow down. Okay, by reducing the window size, because when the window size is small, you're sending very slowly. Let's also reduce the rate of retransmission, which is to increase the timeout interval. When it's twice that long, then we are retransmitting, the half speed. So both of these extra mechanism is to address congestion, which is to do congestion control. And you see here in TCP, the reliable data transfer mechanism is somewhat mingled with the congestion control. And that's why you see in example 3, supposing if this is go back in, then when the timer for send base 92 expires, sequence number 92 and sequence 100 should go out. But instead, only 92 goes out. So let's summarize up to this point the similarities between TCP's RDT versus the go back in. So we see similarity being what? Both of them are pipeline segment, and both use cumulative X, and there's only one retransmission timer, and it retransmits timeout events. We've heard already, unique in TCP is this. The timeout interval is well defined. There's an equation, and there are good reasons just justifying the equation. And we only refresh timer on new ACK. In go back in, we actually refresh the timer even though it's a duplicate ACK. Also, in TCP, that's unique is this. Retransmission, if timeout occurs, we retransmit only one segment. So reducing the sending window size all the way to 1. And the timeout interval is doubled as well. Okay, so exponentially slow in case there are back-to-back timeout events. Now, there are more differences. First one, delay ACK. Second, fast retransmission. So these are the two extra mechanisms in TCP that's related to reliable data transfer that we need to talk about. And what's coming next, a big part, we're going to talk about TCP's congestion control more seriously.
All right, so TCP's congestion control is coming up next week. Okay, we are yet to talk about the other side of TCP's RDT, right? So far, what we've looked at is the sender side RDT. And you see that it's very similar to go back and sender, but there are some differences. And that's because we need to consider handling congestion that might happen in the internet. And we want to be extra conservative, okay, dealing with the congestion. Now, the receiver side of the finite state machine, okay, there are also two differences to the traditional go back in. The first is this. Now you heard, right, I think yesterday, in TCP spec, there's no mentioning of whether we buffer out of order packet arriving at the receiver. And the practice is that we tend to buffer them so that we can conserve some of the network bandwidth. Okay, that's why Polly keeps saying that TCP is go back in with better bandwidth efficiency. So in the receiver side, you will see the first difference. The receiver needs to handle this case where the sequences of the packet arriving might go out of order, and therefore there's a gap, okay, in the sequence number. Okay. Second difference is this. If you recall, two videos before, there's an example saying that if we miss one of the acts, earlier acts, the later act can help acting the earlier act. So we can actually allow losses in some acts, and therefore it's probably not necessary to send act for every packet. So this is the idea called delayed act. So maybe we don't have to send act per packet. We can delay the act and having, for example, every two packets arriving sending just one act. That will further reduce the need of bandwidth sending act back to the data source. Okay, so TCP receiver, the delay act mechanism.
This is the delayed act. So this is the mechanism implemented at the TCP's receiver. Right. Now, in order to contrast TCP's receiver to go backend's receiver, let's bring back go backend receiver's finite state machine. And here it is, the go backend's receiver. There are only two events. First is getting a packet from the network layer, and it's not corrupted, and it's carrying the expected sequence number. Hey, this is the data packet we're expecting. So extract data out, pass it out to the application layer, generate the ACK packet, send back the ACK packet, and then increment the sequence number. So this is in fact the only significant event that we're expecting. All the rest, what the receiver of go backend does is just to send back the same ACK that has been generated previously. And back to TCP's receiver. So the first two events in TCP's receiver are these. Let's read through it a little bit. Arrival of in-order segment with the expected sequence number. Arrival of in-order segment with the expected sequence number. So both are events that's similar, right, to the significant event in go backend's receiver. Data arriving, not corrupted, and carrying the expected sequence number. So good news. We're supposed to generate ACK and send the ACK back. But at TCP's receiver, okay, how we send the ACK back depends on the second condition here. So in event number 1, when all data up to the expected sequence number are already ACKed, okay, then we do one thing. If there's one other segment has ACK pending, meaning, hey, that segment there, we should be sending an ACK out, but it's actually pending. We haven't sent it out yet. Then we do this. Okay. Now, some of you might have guessed, yes, TCP's receiver here is trying to do sending one ACK packet per 2 data packet received. So if all data up to the expected sequence number have already ACKed, that's delay sending of this ACK. Okay. So that's wait for the next segment. When the next segment arrives, then we send the ACK. Otherwise, that's just wait for 500 milliseconds. When this 500 millisecond expires, yeah, we have no choice but to send the ACK for this data. So you see here, this is the other condition. When there is a back packet coming in and there is already one data packet that is supposed to be ACK, but the ACK is pending, which means it's waiting for the 500 millisecond. Then we immediately send one ACK, and this ACK here carries the sequence number of the later segment. Okay? And because the ACK is cumulative, so when that ACK comes back to the data center, it's going to clear both this packet and this packet. The third event is more like the default event. Okay? The similarity, however, is more the action being taken. Okay? So when we receive a segment coming in that is out of order, meaning it's carrying a sequence number that's higher than the expected sequence number, then we will buffer the packet. So as a result, we detect the gap. So let me illustrate so that it's a bit more clear. Okay? Previously, we have received multiple packets, okay, and they are arriving in order. But suddenly, we get a packet that is out of order. It's not quite what we're expecting here next. So there's a gap in the sequence number of the packets received. In that case, upon receiving such out of order segment, upon detecting a gap like this, we send duplicate ACK, the old ACK that has been generated before. This ACK here is then carrying the sequence number of the latest packets received in order. The last event is this. Okay. Related to the gap we might see in TCP's receiver. So if a segment comes in that partially or completely fills a gap, then we generate a new ACK. Okay. The sequence number in the ACK here will be still the latest packet arrived in order.
So this will acknowledge all the packets before that.
All right, that takes us to the first quiz today. It's quiz 24. So far, Polly showed the table illustrating 4 kinds of events the TCP receiver will handle. So quiz 24, Polly will show you the finite state machine of the receiver. Okay, and you'll see which transition corresponds with which event roughly. So let me walk you through. The first transition is down here, T1. It is for the receiver to receive a packet from below, and it's not corrupted. Okay, and it has a sequence number that is exactly what the receiver is expecting. Okay, and it does not fill a gap. So it is definitely not the 4th event, right, in the receiver that you just heard. And there's nothing pending. Okay, it's a little bit unclear what pending means here. Pending means whether there's a delay act timer pending already. Okay, and there's no timer pending. Okay, this means this is the first of the 2 data packets. There needs to be an act to be scheduled. So in this case, we take the data, extract the data, and pass it up to the application layer. We generate an act for it with the checksum and everything. Okay, but the send packet here is kept. Okay, for this long. Start a timer for 500 milliseconds. Oh, some of you might guess T1 is exactly event 1, right? If there's no pending acts to be sent, you start the timer. Of course, you increment the expected sequence number just like the other receivers, go back end receivers or selective repeat receivers. And you set the pending true. Oops. Excuse. Sorry. Yeah, a lot of times I try to mute the phones, but obviously today I forgot to mute the phone. All right, so yeah, pending true means with this now a timer schedule, then there's a act pending to be sent. And we just need to wait for 500 milliseconds in case no more data arriving, we'll send it out. Okay, so T1, straightforward, corresponds to event 1. Now T2 looks very similar. Receive a packet from below, it's not corrupted, and it has a sequence number that is expected. Cool. And it doesn't fill the gap. So obviously this is not event 4. And there's already an act pending. So cool, this is what event 2 exactly. You extract data, pass it up to the application layer, you generate an acknowledgement with checksum and everything, and you send this act packet, okay, instead of this one, okay? But hey, guys, you might be thinking maybe it's not necessary to generate this one. No, it is still necessary, right? In case this one doesn't come, this send packet will still need to be sent after the timer times out. So, of course, we increment the expected sequence number, right? And we say pending will be false this time. And we remove the timer that we have started earlier here. Great. So we see T1, T2 is a pair that corresponds to event 1 and event 2. Now, T3. Receive a packet, it's not corrupted, and it has the expected sequence number. Cool. But this time, this transition is considering this condition. Fill gap being true. So both T1 and T2 says fill gap false. What does this mean? This means there are no out of order packets being buffered later. So this packet arriving does not fill a gap partially or fully. But this event then says, yeah, we fill the gap. Hey, yeah, this is event 4. In case we fill a gap, what do? This is still a good packet. We extract the data out, pass it up to the application layer. We generate an act for this data. Okay, and we send this data. right? Event 4 says, as long as it's filling the gap, we send an ACK no matter what. So we don't start a timer or check whether there's an ACK pending. Expected sequence number, do we increment it that easy? No, it really depends on how big the gap is filled. Okay, so it might need to be the highest sequence number in order plus 1. Yeah. So pending equals false. We will remove all the timers, okay, as well. All right, so this is T3. Now there's one more. Hey, this is default. Okay, so everything else goes here. We just send whatever the egg packet that has been generated before. So sounds like this is where we send duplicate egg, right? If there's a packet arriving out of order, which means the sequence number is not expected, we do this. But if a packet is corrupted, yeah, so all these 3 cases consider packets that are not corrupted. So if there's a corruption, we also do this. Duplicate egg. Just like go back in. Okay. And in this case, we do pending, false, and hey, remove timer. Yeah, so we don't have an event that handles timer timeout. So in case the timer times out, there's no transition says timeout. But if we have a default here, yeah, so we send whatever the packet has generated earlier and yeah, change the pending to false and remove timer, just like this. All right. So these are the 4 transitions in TCP's RDT receiver. I know you guys can wait. Very good, guys. You guys pick up things really quick. That's good for you. So now the questions. Q1 asks, which transition, oopsie. Yeah, sometimes I'll be mistaken. Yeah, I want the cursor going to the other screen. So which transition is delaying X and why? Very easy, right? Q2, which transition sends duplicate X? And why? Okay, so you need to tell me which transition and also tell me why you think so. And Q3, so this one is also obvious. Q3, which transition sends new X and why? Okay, I have to say, Q3 is a little bit tricky. Q3 is a little bit tricky. Multiple transitions send new X. All right, hey, I know, you guys can't wait. Let's go to the score space. Yeah, and I don't know, did all of you? Okay, so I guess many of you have already answered the questions. Let's see what you guys come up with. By the way, for this question, I do not intend to take the quick solvers for bonus. Okay, so I'm thinking correct and thoughtful answers for bonus. Let's see. Team 9 says T1 is the transition that generate that delay X. Yes, that's correct because we have a timer there. Obviously, this is perfect. Which transition sends duplicate X? Obviously, T4, right? Because otherwise, all the other transitions generate a new X. And okay, for Q3. T2 and T3 generates new X. T2 and T3 generates new X. Yeah. T1 generates a new X, but it did not send, right? Yeah, so you know what? Team 9, you're correct. T1 does not send new X. But Team 9, you're missing one more transition that sends new X. I know some of you actually were patient enough to hear Polly explaining T4. You see, T4 also changed the pending status and what? Remove the timer. Which means the timeout event from T1, when it occurs, it will trigger T4, the default transition. And that packet there, scheduled by T1, is that a new packet? It is. So that new packet scheduled by T1 is sent at T4 event. All right, let's see who gets it right. T1. You see T3, Sylvain, T3 sends a new egg. Okay, it's not a duplicate egg. All right, let's see. T1. Okay, so Tao was thinking the same as Sylvain. Same for Yongxiang. And yeah, when you fill the gap, you send a new egg. When there's out of order arrival, you send a duplicate egg. So even though there are packets of arriving out of order, but later in sequence, when you receive packets that fills the gap, you still send a new egg because all those packets trigger sending of duplicate eggs. Let's see. Q1. The answer is T1 because it starts a timer, and yes, exactly. Q2, T4 because it will detect segment that is out of order and send duplicate eggs. And Q3, T2, T3, and T4, exactly, right? T2 sends a new egg because there's a second data arriving, and there was already an egg pending. So with 2 eggs now, T2 sends a new egg and change the pending status to false and remove the timer set when the first data arrives or when the first egg was scheduled. The reason for T3 because there is the gap that is filled and the egg are sent. Yeah, when the gap is filled partially or fully, there's a new egg generated. Yeah. I know you guys might be thinking that if there are packets out of sequence arriving, then the egg for those are already sent, right? Then you send the egg you send when you fill a gap must be an old egg or duplicate egg. No, you were thinking a little bit too selective repeat. Yeah, and go back in. Out of order arrival, you drop it and you don't change the egg sequence number. In TCP, it's go back and like. So out of order packets will be buffered, but that doesn't mean the egg will be advanced. Okay. The sequence number of the eggs will be advanced. And T4, new data sent when the timer of T1 expires. Great. Okay, so Team 5, thank you for listening to the end. Yeah, so a finite state machine sounding easy because Polly has made it sound easy in the lectures, in those short videos. But if you look into it and follow through, you will see that it can be tricky still. Okay, there. And Maria says T1. T3, yeah, and Q3, T2. Okay, so Team 3 is agreeing with some other teams up there. All right, so yeah. Okay, so far only Team 5 fully correct. Let's see, Team 4. T1. T4 is the one sending duplicate eggs. There you go. Team 4 is the second one correct. And Anthony, yeah, you guys are the third one being fully correct. Okay. Yeah, so for the rest of the teams, okay. Hey, you want to correct back? There you go. Yeah, I guess the confusion is very good. I see Sylvain has made the correction. Very good. Okay. All right. Yeah. Yeah, so I guess Q2, this should be straightforward, but I see many of you answer T3. Yeah, that's probably because you thought that filling a gap means you send duplicate egg. No, it's not. It's more if you receive a packet and you see a gap there, then you send duplicate egg. But this is a packet arriving but fill a gap. Okay. Great, Sophia. I see that you updated that. Okay, Maria, same thing. Filling a gap sends new egg. Okay, Nicholas, very good. And Qingtao. Okay, very good. Okay. Okay, so team one. Okay. Team one, the reason is not exactly right. For T2 and T3, the eggs are sent directly. Not all of them sent through T4. So T2 and T3 sends egg directly. Only the egg scheduled by T1 is sent through T4. All right? Okay, so guys, I guess this one is better off appearing in the exam so that you guys will try to figure things out. Okay. Yeah, so I know that some of you couldn't wait and try to answer. That is not bad at all. But in this quiz, you see that it makes a difference if you pay attention to Polly describing the transitions first. Good. And you know what? It's time to take a break. It's currently 11:11. We'll resume the lecture 11:21. Okay, so let's take a break. And guys, try to figure it out. Scroll back the video a little bit and watch Polly's explanation of the receiver finite state machine. welcome back. Yeah, let's move on with the lectures. So we're still in TCP's reliable data transfer mechanism. The last trick, last improvement people add to TCP's RDT is this thing called fast retransmission. It has something to do with when we receive duplicate AGs. In go back in, we just simply wait until timeout. But in TCP, people feel that it's better to retransmit a little bit faster in that case. So that is what this video is about. Last is the fast retransmission mechanism. In order to explain why we need fast retransmission, let's go back a little bit. When we were describing, when TCP sender experiences a timeout event, it's what? Dropping the window size down to 1 and setting the timeout interval to twice the current value. Okay? Because TCP sender, they actually consider a timeout event being network being congested. Now this is very reasonable when there is a congestion. TCP sender here being a pipeline RDT sends often segments back to back into the network, hitting the congestion point. Router there, buffer full, no more space. All these packets arriving back to back gets dropped. Receiver won't be sending any AGs coming back. Sender has nothing to do but to what? Take the timer that started when we send the train of packets out. And so eventually, timer expires, timeout event triggered, and therefore we slow down very drastically. Okay. So congestion, and we slow the sender down drastically, makes sense. But what if the packets go out did not hit congestion point? Okay. And we just have a random loss packet in the middle of it. What does the receiver do there? Yeah, it's going to get packet in order, and then a random loss. All the subsequent packet arriving out of order are going to generate duplicate AGs coming back to the sender. If you recall TCP sender, when there are duplicate AGs, what do? We ignore. So sender there will still take the timer and have a timeout event eventually. And we are still what? Reducing the window size to 1 and set the timeout interval to twice the current value. That's overdoing it, isn't it? And that's why we have the fast retransmission mechanism. Because if we see multiple duplicate AGs, and when there is a higher number of them, then you will probably guess there is a random drop right before the duplicate AGs, okay? Or at the first unagged segment. So that is exactly what TCP fast retransmission is doing. When sender receives multiple AGs for the same data, to be more precise, it's triple duplicate AGs. Then we resend the unagged segment with the smallest sequence number, because this is very likely the lost packet there. Okay. So then we don't have the timeout interval being long problem, right? Because we'll be waiting a long time to retransmit just this sporadic loss. Okay. And this is to exploit the characteristic of TCP being also pipeline. We send back-to-back segments. In case of sporadic loss, non-persistent loss, we could observe number of duplicate AGs coming back to the sender and resend the packet real quick without waiting for too long. And this example illustrates triple duplicate AGs. Host A here is the data sender, host B here is the receiver. So window size warrants that we send 5 packets in one train. Let's say packet number 2, sequence number 100 is lost. Then this is going to generate AG for sequence number 100. But this one is lost, so it's not going to generate anything. All these subsequent packets, it's going to just, trigger the receiver to send the same AG back to back. So sender here receives the first AG for 100. And this is the first duplicate AG, second duplicate AG, the third duplicate AG. And this is when we begin retransmitting the first, the smallest sequence number that is unagged. And so TCP sender's pseudocode needs to be modified. And the only part needs to be modified is this event, when we receive an AG packet from below. Okay. First of all, we extract the sequence number in the AG packet. And this is the case when the AG packet is new. And this is the other case when the AG packet is not new. So in here you see, we increment the count of duplicate AGs. Okay. For each duplicate AG, we increment this by 1. When the count for duplicate AG is exactly 3, then we resend the segment. So this is fast fast retransmission of a lost packet. And then, of course, drop the count back to 0. This is the last slide to summarize TCP's RDT. TCP's RDT is essentially go back in, so the base is go back in. But TCP being something that we actually need to implement and seeing running, defines very clearly the equation to derive timeout interval. TCP is also a little bit more performance conscious, so timer will only get refreshed when there is a new ACK. When there's a duplicate ACK, timer does not get refreshed anymore, unlike in go back in. TCP there is also not only doing reliable data transfer, it also does congestion control, flow control, and everything else. Therefore, we see when there's a timeout, the retransmission window is only dropped to 1, and the timeout interval could be doubled. More unique in TCP RDs. TCP receiver here is also trying to reduce the effort of sending ACKs. TCP receiver here also tries to buffer that arrives out of order. So memory is required as well as the TCP receiver, unlike the go back in receiver. TCP implements also fast retransmission, so for certain patterns of loss, we get to recover faster instead of waiting always for a timeout.
All right, so RDT of TCP. Okay, finally complete, and we move on to just the last other functions in TCP that's related to RDT. First is flow management.
And that takes us to the flow control of TCP. Allow me to explain. Okay, so this is again the protocol stack. This is the application layer, transport layer, and the network layer. And packet is coming in from below like this. So network layer is going to pass the segment to the TCP receiver right here. Okay. If everything is okay, TCP receiver is going to extract data and pass it further up. Okay. What's going on really in the implementation in the operating system is this. That data does not go directly to the application layer process. There's this place here called the receiver buffer. So the packet being extracted is actually temporarily stored here, okay, waiting for the application layer process to fetch it. So the application layer process is going to remove data from the receiver buffer. Okay. Just like the TCP receiver here is going to push more data into the receiver buffer. Okay. And TCP flow control is needed when the application is drawing data slower than TCP receiver there, delivering data up. Because when that is the case, the buffer space will be what? Occupied. More and more and more and more, because outgoing slow, incoming fast. And eventually the space is going to be exhausted. The subsequent data will be dropped right there between TCP receiver and the receiver buffer. And this is super bad because TCP here is working very hard to try to get this packet in. Okay. So flow control there is this. For the receiver to tell the data sender, slow down a little bit so that you will not be overflowing the receiver buffer by transmitting too fast, too much. And the way flow control works is this. It works by tracking this variable, RWND. Okay. In the operating system, there's this receive buffer. This is well defined, and it's actually the size of the receive buffer space. Now, initially, RWND is going to equal the receiver buffer. Whenever TCP receiver sends data to the upper layer, this RWND is going to be subtracted by the amount of bytes being passed up here. Whenever the application layer process is drawing data out of the buffer, the RWND is going to be incremented by the number of bytes there. So RWND is essentially tracking this, the free buffer space. So once we manage to track the free buffer space, TCP receiver here will advertise the free buffer space by including RWND in the receive window field in the packet header, in the TCP packet header, and send it back to the sender. And that's when sender knows it needs to limit its sending window so that it's smaller than RWND. So you see here at the sender side, the sending window not only is limited by the congestion control mechanism, but also by flow control mechanisms, RWND. And that guarantees the receiver buffer not being overflowed. So we see buffer here. In most of operating systems, when you create a socket, it's set default to 4096. But most of the modern operating systems these days would actually give you different receive buffer space by default. If there's more space, then this is potentially higher.
Yeah, so you see flow management or flow control is relatively straightforward. Yeah, so we communicate how much receive window, how much buffer is left in the receive window. So the sender can also slow things down. Last is connection management. Okay, so TCP being a connection-oriented multiplexing service, we need to set up a connection first, set up the channel first, and that's the beginning of the connection management. When the TCP connection closes communication, we also tear the connection down. So the establishment part is called the three-way handshake. The closing part, however, can be initiated by either the client or server, okay, and they can work independently. Okay. There was before we play the video, there was a question from Justin. Yeah, so in some cases where we have duplicate 80s and then the packet 100's ACK comes back, in case ACK 100 arrives before the third ACK 80, the third ACK comes back will still initiate fast retransmission. So you're right, Justin. And so the better way to do it is to null the count for ACK 80 when ACK 100 arrives. So the pseudocode definitely did not cover this case. Okay, but as a network engineer, good that you think of this boundary cases, and of course you can add lines into the code to handle the situation. All right, and now we play the video of connection management.
Last is the connection management of TCP. There are two parts. First is establishing connection. Second, breaking a connection. Let's talk about the process of establishing connection. It needs to be done before exchanging data, and the process is called a three-way handshake. Okay? At the end of the process of three-way handshake, we would establish a connection, or aka a socket. Okay? So once the socket is established, two ends can begin sending data to each other. So the socket establishment process is also exchanging some number of parameters. Now this is crucial because later on, when the client over here on the left is trying to send data, in the packet header there, it needs to carry a sequence number. When that packet arrives at the receiver, which is the server is going to examine the sequence number in the packet header to decide whether to extract the data out and pass it up to the application layer. And when do we extract the data? Only when the sequence number equals the expected sequence number. Okay. So there is a certain parameter at the receiving part, okay, that needs to be initialized. Okay. And because either side can be sending data, receiving data. So server here would also need to tell the client what is the initial sequence number server will be using. Therefore, the client can set the expected seek num accordingly. And this illustrates the three-way handshake. Client, server, both initially just listening, and client at some point wanting to request some data will then initiate connection, dial into the server. Okay. So it's gonna choose an initial sequence number to tell the receiving of the request messages. And it's gonna be sent in a TCP sync packet or sync message. Now, if you recall back in TCP packet format, in the header part of it, there are a number of these flags one can set. So sync packet is the packet with the sync flag being set, the S flag being set. That is also called the sync bit. So that bit is going to be turned to 1, and the initial sequence number is going to be in the packet somewhere. Okay, and that packet is going to arrive at the receiver, which is the server. So client, after sending the data, is going to be in the sync packet already sent state. Now, the server will then in the sync received state. So server here will be doing two things. First, send back an ACK, right, to tell the sender of the sync packet that the sync packet is received. Okay, so sync ACK is such a packet. That is to ACK receiving the sync packet. Right? The server here will be doing yet another thing. Okay, choosing its own initial sequence number, and let's say it's Y, and this Y will be stored somewhere in the sync ACK packet as well. So you see here, this packet goes back, and the sync ACK packet is going to have the sync bit on as well as the ACK bit on. Okay. And in sequence number, server tells the client it's going to start from Y. Okay. And this being an ACK packet is going to tell the sender of the sync packet that, hey, the next one I'm expecting is X plus 1. All right, so next seek num is already set to X plus 1. And lastly, when the client receives the sync ACK back, so it's going to receive the sync ACK. At this point, the client is sure that the connection is established. Okay? And so server is live. The last thing the client needs to do is just to acknowledge receiving the sync ACK. Okay? So it's just an ACK packet, and the ACK number is Y plus 1. Yeah, because this guy here observing the initial sequence number of the server is Y, then therefore the next seek num is set to Y plus 1. And that number is also shown in the ACK sequence number. And so server finally receiving the ACK is sure that the client is live and the socket is now complete and in the establishment state. The closing process is actually not exactly three-way. It's actually independent. The client can initiate the closing process. The server can also initiate the closing process. And the message exchange is just a pair of fin and ACK. So a fin packet out from the one who wants to close. And ACK will come back from the one receiving fin. Right? So there could be simultaneous fin exchange between the client and the server. So the client and the server are both exchanging data. And finally, the client here says, okay, I've finished sending all my data requests, so I'm ready to close. Then it's going to enter the no longer send but can receive data state. And that is called the send fin, and now wait for the rest of the data to come in. So you see here the fin packet is the packet with the fin bit on. Okay. Server here receiving the fin packet sends back an ACK. Okay, so ACK bit on and then ACKing the sequence number. Server here will enter the close wait. So server knows now that the client wants to close, but it's not quite yet closable because client setting close is just that finishing sending request. There could be some more data waiting to be sent here. Okay, some more ACKs waiting to come back here. Okay, so server needs to finish all these other data that's remaining. But client here receiving the ACK for the fin is pretty much done and just waiting for the server to say everything is already sent, so you're okay. So finally, server says, done with all the data. Okay, so sending fin. Client here is receiving the fin, sends back the ACK. Okay, saying good, that's close. Server can now close safely, no problem. But client here needs to wait 2 maximum segment lifetime before it can really close. And this maximum segment lifetime is usually 60 seconds long. Can you guess why? Why the client needs to stay so long until it can really close the connection?
Yeah, so I'll let you ponder why so long. And hey guys, we're done with TCP's RDT now. We'll move on to the second major topic in chapter 3. So as you recall, one of the major functions in transport layer is congestion control. So this next video, Polly would describe why there's congestion control and what's wrong when you run into congestion. Okay, so this video relatively short. Okay, 2 minutes.
Principles of congestion control. Now the section title sounded a bit like we're going to talk about these general mechanisms to do congestion control. Well, but no, in 3.6, what we're going to talk about mainly are what's causing the congestions to occur. What is so bad about having these congestions? So hopefully from the discussion, you see a little bit the nature of congestion and the design elements of doing congestion control. Congestion is this thing, having too many sources sending too much data too fast into the network. And by network here, I actually meant the core of the internet. Right? So congestion here sounds a little bit also like the problem we see in TCP, such that we need flow control. The situation there is that the TCP source sending too much data too fast into the receiver buffer. So the congestion there occurs at the receiver. And the resources that's being exhausted is the receiver's buffer space. Now when we're talking about network congestion, congestion is occurring here, routers. And these are the machines that are in the core of the internet. And the resources that we are exhausting there when congestion occurring are these, the buffer space. So router buffer is the resource that we're trying to handle. Now when we are all sending data into the core of the internet, you see that these buffer space can quickly be exhausted. If not, hey, we will have to wait a long time, or these packets will have to wait a long time, right, until they get served. So what's bad about having congestion is this. We see packet loss when the buffer overflows, or long delays when there are lots of packet waiting there to be served. Congestion there is one of the top problems in computer networks, just like reliable data transfer, and probably a little bit more serious than reliable data transfer these days. Coming ahead is a series of these scenarios, growingly more general, and hopefully by the end of the discussion, you see congestion is something that's really bad. You could invest a lot of time, a lot of resource, but you ended up having nothing.
Yeah, so congestion is bad. And Polly will use three videos, essentially three scenarios, gradually telling you that congestion is really bad. And these three scenarios will growingly more realistic. Okay, so first scenario, rather simple, only 2.5 minutes. It's a not realistic scenario at all. We are assuming that each of the routers in the network will have infinite amount of buffer space. But you will still see when we have congestion. What is congestion? Too many sources sending too much data too fast into the network. Okay, so when you have a router, even with infinite buffer, sending all that much traffic into the network will still create a problem. And the problem is that the delay grows longer. And that delay is called the queuing delay, if you recall, okay, back in chapter 1. So the first scenario, 2.5 minutes.
Scenario 1 is this. Okay, you see here, we have two senders, host A and host B, two receivers. Okay, so two servers receiving requests, I suppose. So two senders, two receivers. And we do have a link in the middle. And the capacity is what? R. And there's a router on the link and carries infinite amount of buffer space. Cool. So what that means is that there are no packet drops, because it just takes a long time for the packet to go, but they're never dropped because we have infinite amount of buffers. Now let's assume that there's no bit error, therefore there's no need of retransmission because there's no packet drop and no bit error. Okay. Now let's use lambda here to denote the rate host A and host B are injecting data into the network. Okay, so host A and host B are actually raising the rate, okay, as time goes. Let's use lambda out to denote the amount of data that arrives at the receiver. Now, when lambda in is really low, starting from here, when we increase lambda in, the more data we send in here, the more data comes out here. Okay, so lambda out will actually increase accordingly. But this will only go up to here. When we exceed the link capacity, because there are two flows and link capacity is R, so each flow gets only half of R at best. That means lambda out here can only, at best, being R divided by 2. So even though lambda in continues to send more, but no, we hit the limit, hit the ceiling here because resource is limited right here. Okay, we don't get to push more out. So increase sending rate, receiving rate accordingly. But here, even though we're increasing the sending rate, but the receiving rate remains the same. Now, the delay is going to show this way because when lambda in continue to increase, as you reach half of R, it reaches also the link capacity, right? Because this is also half of R, this is also half of R. And so at here, it's R completely occupied. So when we approach the link capacity, the queuing delay is what? Yeah, approaching infinity. So the first bad thing you see already, long delay, when we send a lot more data and more than what the network can accommodate.
All right, so congestion bad, long delay, even in a unrealistic scenario. Now the second one, now let's assume there's a finite amount of buffer, and you will see another issue rises, and that is packet losses.
And scenario 2 is actually very much like scenario 1. The only difference is this. The buffer space in the router there in the middle now has only finite amount of space. So in scenario 1, we have infinite buffer, so we don't have packet drops. Right? So what's bad about that scenario is just we will have long delay. But now in scenario 2, we have finite buffer space, so potentially we could have what? Packet drops. So potentially we need to retransmit packet. And retransmission here is at the TCP layer. So if lambda in is what the application layer processes generating the data to send out to the network, that lambda in prime denote the amount of data the transport layer needs to send into the network in order to complete the job. Okay? Then we'll see lambda in prime should be greater or equal to lambda in, because it should definitely contain the amount of data we need to send out, and plus potentially retransmissions of some of these data. Right? Lambda in, lambda out, the same thing. At the application layer, lambda in is going to be very much like lambda out. How much we send out, in the end, at the end of the time, lambda out is going to come out. And that was just to describe scenario 2. Now, let's assume the sender knows perfectly well when the router buffer is available. Okay, so sender sends data out only when there's buffer available here. So no packet drop. Okay, the scenario goes like this. At the transport layer, now we keep a copy of the data just in case we need to retransmit. But the packet will arrive at the router because there's free buffer space, so it travels through the network, reaching the destination. Okay, and that goes back and we remove the copy. Right, so this is when the sender has perfect knowledge of the routers in the middle of the internet. Now in this case, there's no need of retransmission either, so lambda in prime is essentially the same as lambda in, and lambda in is essentially lambda out. So you see the same curve. We could have lambda in increasing, and we get the same lambda out up to the capacity of the link. To be more realistic, let's assume sender does not know whether the buffer space in the middle here is going to be free or full. Okay. So we'll have packet loss this case, because when the packet arrives at the full buffer, it's going to be dropped. And in that case, they will have to resend the packet. So packet arriving at the transport layer, at the sender side of transport layer, we keep a copy. Now, that packet arriving at the router sees buffer full, so drop the copy, and the sender there waits for some amount of time and retransmit. And this time, it happens to be free and it passed through. Receiver there receiving the packet sends back acknowledgement and removing the copy of packet here. And you see, at the application layer, there's only one packet being sent. But in the transport layer, we send 2 times the same copy. So lambda in prime, the output rate at the transport layer, it's definitely going to be higher than the output rate at the application layer. Now the output rate at the application layer for TCP is going to give you the same thing at the receiver end. Therefore, you see lambda in prime versus lambda out. It's going to be lambda in prime higher than lambda out. So in the end, even though the lambda in reaches its capacity, half of R, okay, but we don't get exactly half of R out here, because some of these half of R is going to be used for retransmission. So this margin here, unfortunately, is used for retransmission. So the actual amount of data coming out, less than half of R. And you see here, the bad thing, number 2, we have retransmissions when there is congestion here. To make it even more realistic, we know earlier when the buffer is full, the packet can be lost. The thing is that at the sender side, in order to detect if there's a buffer full, if there's a packet loss, we set up timer as well. Okay, so these timer can go out prematurely and therefore sending copies while we don't really need it. So it's illustrated by the animation here. Data coming from the application layer process, we keep a copy at the transport layer sender just in case we need to retransmit. Now let's assume that the buffer is free, but in case the timer is too short, we time out prematurely. We ended up sending 2 copies of data here, okay? While only one copy of it will be arriving at the application layer. So lambda out remain the same as lambda in, but we see here, the lambda in prime, this is gonna be higher than the lambda in prime in the previous assumption, where we do not assume the timer can go out prematurely. So the performance of lambda out here as lambda in prime increases is going to go slightly worse. The margin here is going to be bigger because what? Lambda in prime here, we need to take into account the retransmissions. Now we also need to take into account the duplicates that are not really necessary. So we see delay being bad, retransmission being bad, and what's even worse is that we could have unnecessary retransmission. Now if you think about it, congestion, we see that having packet loss, having delay, not good. But to address packet delay issue, to address packet loss issue, we need a retransmission mechanism, the RDTs. As a result, what? We are actually generating more traffic into an already congested network. So the cost, okay, of congestion is actually not that trivial. Okay? It's not just that the delay rises, it's not just the loss increases, but also the traffic being dumped, injected into the internet also increases. So in the end, the internet is doing even more work, while the throughput is not getting better and sometimes even worse. As you see, the margin here is bigger than the previous case.
All right, so it's not just packet loss, okay? It's also that you might do unnecessary retransmission, meaning you do work and more work, but not ending up having more result, okay? So this is very often why, guys, this is about the time that you completed the first exam or the midterm exams and you're seeing the results, okay? The thing is that towards the end of the semester, okay, when there are too much assignments you need to submit, too much that you need to study, okay, you will also be congested, and here is where you get congested, okay? Sometimes you will find, even though you try to spend more time studying, but you don't get better results, you see? So pay attention to how internet does congestion control. You might learn something about how you control yourself so that you are more productive than less productive in the meantime that no matter how you try. Okay. Now there's a third scenario. Congestion is super bad. So we heard congestion is bad because delay higher. Congestion is bad because we will have loss. Congestion is bad because we will have unnecessary retransmission. Now, congestion is bad because on the internet, traffic will cross each other. Okay, one bad connection might influence many other perfectly fine connection. Okay, so in the third scenario, you will see a network that's more realistic, where you have sources here, there, and receivers here, there, and they could be crossing each other.
If you think scenario 2 is bad already, where we do more work, right? Lambda in prime increasing, but lambda out increases at the beginning but saturates toward the end. Okay, so beyond certain point, the more work you do, you don't get more results. But here, I'm going to show you an example. Yeah, at the beginning, the more work you do, the more results we get. But in this scenario, the more work you do, you might end up having less results. And the even more work you do, the even less results. And here's the scenario. We do have 4 senders now, or 4 hosts, A, B, C, D. Okay. And each of them is generating a flow traveling multiple hubs. So this is one hub, this is the second hub for the red flow. Okay. So multiple hubs. And yeah, we might run into buffer full situation, therefore we could have packet drops, and therefore we do need a transport layer mechanism to try to do retransmission. So similarly, we have the lambda in, which is the input rate from the application layer, and lambda in prime being the input rate of traffic into the network from the transport layer. Okay. Now let's focus on the red flow coming from host A and the blue flow coming from host D. Okay. And these flows will increase the sending rate lambda in. And therefore, lambda in prime will also be increasing and sometimes increasing faster than lambda in. Now what's going to happen when lambda in and lambda in prime increases? Now, at the beginning, you see the red flow, the red packets coming into this router here. Okay? And as the rate increases, the buffer space here is going to be occupied by the red packet, just like the blue packet in the meantime, coming into the first hop router and occupying the front sections of the buffer space in the router there. Now, after a while, the red packet is going to come out and enter the second hop, just like that. Blue packet is going to come out and enter this router here at the top. And the blue packet will be coming in to compete with the red packet that is already occupying most of the buffer space. Okay, so this is already pretty full when the blue packet just arrived. Okay. And as the lambda in increases as well, as they both approach a half of R, you see this. The buffer space is going to be very full and quickly. Red packet will be dropped, but blue packet will be dropped even more because very few of these blue packets get into the queue and have a chance to go out, finally reaching B. So as lambda in prime increases, the arriving blue packets at the upper queue here, most of them get dropped, and therefore the throughput very small. So you see right there in scenario 3, the blue flow, right, when lambda in or lambda in prime is small, right, when the network is not saturated, when the buffer does not overflow, then the more work we do, the more output we get. But as it approaches half of R, we see blue flows, blue packets gets dropped a lot. So originally, not so bad, but in the end, when buffer flow could occur here, blue packet gets very little chance of coming through, and the throughput is going to be even lower, okay, than when the lambda in here is small, okay? Really bad. So that is another cause of the congestion. Because what? The bandwidth that is transmitting these packets when they're traveling upstream, okay, it's all wasted. Okay? The amount of waste is actually not quite comparable to retransmission or unnecessary retransmission. Those are probably very small. Therefore, in the lambda in and lambda out plot we saw earlier, the margin is very small. But here, the upstream bandwidth, those are all wasted. Okay, so the amount of resources we are wasting here could be very high. Okay, so the hidden cost here, waste of all these upstream bandwidth resource, and this is a big cost. So, message here, congestion, really, really bad. But what can we do about it?
Okay, so I guess what you can see, the big message is congestion is bad. So the last scenario is just to say that because traffic travel a long way to the destination. So it might go really well at the beginning, but in case there's a bottleneck and there's a congestion somewhere happening in the middle of the pass, all these prior efforts could be wasted. All right. So all these scenarios, the bottom line is just to let you know that congestion is super bad. Okay, that's why it's one of the top 10 problems on the internet. Now, let's work on a quiz. Okay, before we start, how we can address this issue, having congestions in the network. So this is quiz 25. Guys, wake up. So this is highway. This is a highway that connects Taipei City to the airport line, to the airport. So assume that you are a Uber driver, okay, and mainly driving passengers between the city, the downtown, and the airport. And so this is highway number 1. Okay. And today, it's badly congested as you are taking a passenger to the airport. So Q1 asks, can you give a couple reasons why there's a congestion there happening on the freeway? Q2 asks, how are you going to tell the other Uber drivers to not come over to the highway so that the congestion can be eased?
okay, or so that the other Uber drivers will be able to take the passengers smoothly, okay, in time to the airport by avoiding this pass. So the reasons of congestion and how you'll be able to inform the fellow Uber drivers. Okay, now let's go to the discourse space. Yeah. And guys, this is one of those open-ended problems. Okay, let's see. How about 4 minutes of time thinking and 1 minute typing things up? So I'm looking for thoughtful, unique solutions for bonus. It's 12:01, so Polly will come back and check the answers 12:06. Let's start counting time. All right, let's see. I see some students. Yeah. Okay, Hong Yu, I believe that's the pronunciation. Says, hey, the reason of having congestions on highway is having too many cars, or the road is not big enough or wide enough to accommodate the traffic. Someone driving slow, of course. Yeah. And how do you inform the other drivers to avoid the route? Texting, calling, yeah, definitely. Very typical solutions. Let's see, Miguel, representing team 3, heavy traffic. Yeah. Oh, constructions. Mm-hmm. Usually having constructions, right, the number of lanes on the highway will be reduced. That means a lower amount of capacity. Similarly, right, for car accidents, bad weather will slow down the transmission rate, right? And when the traffic goes slower, then likelihood of having a congestion higher if the sources do not slow down accordingly. Sure, Miguel, have you been an Uber driver? Yeah, Uber in-app communication. or radio communications, or yeah, social media. Yeah, so there are so many different types of texting apps. Ah, okay. Was it? Yeah, so yeah, it was a really popular traffic app. So WASE tells the traffic congestion already, in a way. So that way the Uber driver doesn't, so you guys don't need to tell your co-drivers explicitly, right? These guys can just observe from WASE, or observe will dynamically suggest a shorter travel time route. Very good. Great. So let me just say Mark. Great. Very good. Let's see, Maria. Accordion effect, peak traffic hour. Ah, of course. Yeah, accordion effect. Accidents and bad weather. Dedicated radio channel. Yeah, I think in some regions you see the drivers talking through walkie-talkie to other drivers. Apps too, of course. But this is more like having the other drivers spontaneously checking the apps. Many people want to go to the airport. Accident? Yeah, okay. I guess the reasons of having congestions, it's quite common, and we know very well. And we have experienced congestion before on the on the roads, city roads, street, or highways. Okay, so imagine all these could happen on the internet. Yeah. And so something to avoid other drivers or other traffic sources generating traffic going the same way. Yeah, is you need to kind of figure out a way for the internet to tell the sources, say, slow down or take a detour. Okay. Very good. I think you guys have got it. In fact, next week we'll start by talking about the two approaches generally people do. One is to have you guys who are driving or as packet travel through the network, having these switches who observe the congestion, closely to tell, tell the sources to slow down. The other way is wait until the traffic arrives at the receiver. When the receiver observes that, hey, the arrival rate of the traffic is slow, the receiver tells the source to slow down. So somewhere, someone in the network needs to tell the source to slow down or take a detour. Okay, so yeah, probably we use the rest of the time and even the office hour to continue grading you guys' quiz. In the meantime, oh, I see a question there on the chat from Ilu. The user can also directly indicate if there are any problems that haven't been reported yet on WASE. Okay, yeah, sure. So WASE is quite powerful. I also have it installed on my smartphone. At the time I install it, I don't see it working really well in Taipei. I hope that it's doing better now. In Taipei, I use Google Map or Apple Map a little bit more. All right, so great. So you guys got the idea. Congestion really bad, and there could be multiple reasons. And when it's really bad, you definitely want the other drivers to know, either slow down or detour. Okay. Now, with that said, hey, that's all the time we have this week. Before I say goodbye, Maria, are you still online? So if you have questions, please join me on the Google Meet channel here, and the hour coming up is the office hour. And that's all, guys. I'll see you next week. By the way, the beginning of the next week, or actually shortly, about 10 minutes into the lecture next week, we'll have a very interesting quiz where you guys will be interacting with Polly directly by joining also the Google Meet session here. Okay, because it's gonna be a game that we play for that quiz. Okay, and it's necessary that you go on Google Meet so that we can interact in real time. Okay, because you will need to guess something, and I will tell you whether it's right or wrong. And this needs to be going really fast, but that game is because that game is played under time constraint. And guys, the game has two phases. Those who win the first phase. Do we need cameras? You don't need cameras. Okay, you just need to have audio because you'll be saying something. Okay, telling me what the answer is. Okay, with the camera, of course that might help a little bit better, but I think having audio is sufficient. Okay, for that quiz. So those who win the first phase will enter the second phase. And so, guys, you'll be working on a team basis. Okay, so each team will guess the answer. Okay, and those that are closest to the true answer will win the first phase. Okay, and that team winning the first phase will will receive automatically, and all members 5 extra points. Okay, and that is on top of the regular participation points. So 5 extra participation points. Okay, that's on top of the regular participation points you earn by chatting on the YouTube channel or on Discord or sending me email. But eventually, those who enter the second phase and winning, get the answer right, will receive 20 points extra. Okay, so 5 points for the winner of first phase, 20 more points. Okay, for the winner of the second phase. All right. So those who win the first phase and win the second phase, you guys will receive 25 participation points for completing for quiz 26. All right. But I have to say, not every year we have a team that earns all 25 points. Okay, good. And by the way, there will be 2 opportunities, so we'll play the game 2 times. Okay, so those who would really like to know what's going on, hey guys, go back to last semester S23's video recording, the live stream recording. You will get a rough sense how it's like. Okay, and so maybe you can prepare a little bit ahead of time. Okay, great. All right, so that's all for this week. Okay, bye. See you next week for quiz 26. So Maria joined at about 12:17. So let's give the class 3 minutes time to exit the classroom. Bye. To be more creative. Yeah, it's like a self-made red light, Sylvain. Cool, love it. Exactly, you can ping. Cool. Yeah, ask your friends, other drivers, to use the Google Map, definitely. Okay, bye. Okay, so I'm closing the stream now. Okay, bye.